So as I mentioned, the probability of a type 1 error is exactly alpha. That's what alpha is. We decide that if we have a small enough p-value, we're going to reject the null hypothesis because we would have only found a difference in a very small probability. But we still might just have that random sample where it happened by the random sampling, and we would make a type 1 error. So the probability of a type 1 error is alpha, the significance level. So 0.05, 0.01, whatever you're using. Okay? That's why you want alpha to be low. If you take alpha to be 0.05, you have a 5% probability of making a type 1 error, which means you have a 95% chance of not making a type 1 error. Okay? Type 2 is more complicated to think about the probability because if you're wrong, then the null hypothesis is not true, and mu could be equal to anything, okay? Or whatever parameter you're looking at. So you would get different probabilities depending on what's actually true, and we can only compute the probability of a type 2 error in specific cases. And also, we have here on this slide, power is exactly the opposite of a type 2 error. In terms of probability, they're one minus the other. So a type 2 error is when you fail to reject the null hypothesis when it's false. Power is when you do reject the null hypothesis when it's false. So they're the opposite of each other in terms of probability. So power is the probability that we reject the null hypothesis when it's false, and that is 1 minus the probability of a type 2 error is the relationship between them. And so in either case, we can only compute that if we assume that a certain alternative is true. And I'm going to do an example of that next. Okay. So suppose a dairy farmer is concerned with the mean percentage of butterfat in his milk. He wants to take a random sample of 30 units of milk and test the hypothesis. So you have the null hypothesis mu is equal to 3.35 and the alternative mu is greater than 3.35. So let's say we want to have 3.35, whatever the units are here, butterfat. I guess the percentage it says. You want the percent of the milk to be 3.35% or lower maybe, and then we have the alternative that mu is greater than 3.35. So the farmer's concerned with being able to detect that if it happens, and we have to do it in a specific case. So compute the power of the test for detecting an increase if the true mean is 3.4. Assume that he knows that sigma is 0.15, and so on all the z procedures right now we're assuming we know sigma. If you don't, you would use S, and it becomes T procedures that we'll talk about later. So to compute power, it's sort of a two-step process. You have to figure out first what's the level where you would reject the null hypothesis. So you would be doing a test based on the null hypothesis. You would be assuming that mu is 3.35, and you would use sigma over square root of n, so 0.15 divided by square root of 30. And if we use alpha as 0.05 for a greater than problem, we would be rejecting whenever you have 0.05 in the upper tail and then 0.95 to the left of that. So if we do inverse norm, we can find the value where we would reject in that situation. So if I do inverse norm with 0.95 for the area to the left, and then we use mu being from the null hypothesis 3.35, and then we use sigma over square root of n, we get 3.395. Okay? So if he gets any number bigger than 3.395, he would reject the null hypothesis. So that's the value at which you would reject the null hypothesis. Then, to compute the power, we would determine, well, what's the probability that we get a sample mean that is greater than 3.395 if mu is really 3.4? Okay? So if the null is really false and it's 3.34, what's the probability that based on our assumption that it was 3.35 that we would reject the null hypothesis? So we would do the normal CDF from 3.395 off to infinity, 1e99. Okay, so what's the probability that he gets a sample mean that's bigger than our cutoff there, 3.395 off to 1e99, now assuming that the mean is 3.4, because we're going to compute the power if the mean was 3.4. And then we still use sigma over square root of n here because we know sigma is 0.15 and n was 15 in the sample. And we get 0.5724. So computing power is fairly complicated, you see here. You have to first figure out, if you assume the null is true, when would you reject the null hypothesis? And then you use that and the alternative to figure out, well, what percent of the time would you do that based on random sampling? And it turns out here to be about 57%. And then just a few comments on that. We keep going back to sample size. The larger the sample, the better. You got the law of large numbers going for you. So how large of a sample should we take when we plan to carry out a significance test? The answer depends on what alternative values the parameter are important to detect. If you have a specific alternative in mind, you can figure out what sample size you would need for a certain power. Okay? But in general, if you insist on a smaller significance level, you want to take your alpha because you don't want to make a type 1 error. So if you want 1% rather than 5%, you would need larger samples than you would at the 5% level to keep the power. Smaller significance levels require stronger evidence. Okay? If you insist on high power, such as a 99% power, rather than a 90% power or a 95% power, you need larger samples. If you want more power, smaller significance, you need larger samples. Okay? So at any significance level and desired power, detecting a small difference requires a larger sample than detecting a large difference. So the larger the sample, the better off you are, but in practicality, you don't want to take huge samples. And as we mentioned, if you take samples that are too large, you might get a significant difference that's not practically significant. And then I have one last example. Let's go ahead and look at that here. So example of interpreting type 1 and type 2 errors. So I added another one to that. So here's an example. Experiments on learning in animals sometimes measure how long it takes mice to find their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause the mice to complete the maze faster. She measures how long each of 10 mice take with a noise as a stimulus. Okay. So first of all, what are the hypotheses? This is a question I usually use earlier in the class with just setting up the hypothesis, and then we'll look at the type 1 and type 2 error, which I didn't animate. You already see the answers there, but ignore those for a minute. So what are the null hypothesis and the alternative hypothesis? So in this case, let's go back. This is a one-sided. So the mean time is 18 seconds for one particular maze. That's going to be your null hypothesis, which I think I did animate correctly, but you see the alternative already. So we're going to assume that mu equals 18. Whenever you have the equality part, that's always your null hypothesis. The mean is 18. The researcher thinks that a loud noise will speed them up, so they will complete it in less time. She thinks they're going to take less time, so the alternative would be mu is less than 18. So that's an example of coming up with the hypothesis there. We don't have the data to get a p-value here, but let's imagine what would it mean to make a type 1 and type 2 error. So a type 1 error would occur if she happens to find a small p-value, reject the null hypothesis, and be wrong. So if she rejected the null hypothesis, she would be concluding that mu is less than 18, or that the mice are speeding up. So that would be to make the conclusion that the loud noise, in general, for all population of mice here, is going to speed them up in the maze, but to be wrong. So to conclude the loud noise causes mice to speed up when it does not. Okay? It may in the sample, but not in a larger population, would be the type 1 error. Type 2 error would be fail to reject. So we don't conclude what we would when we reject, but to be wrong. So to fail to conclude that loud noises speed the mice up, when in fact it does. So that's a type 1, type 2 error in context.